September 7th, 1942, Neville Island, Pittsburgh. A massive steel hull 328 feet long and weighing over 4,000 tons sat poised on greased launching ways above the Ohio River. The vessel had been assembled in just 14 weeks from components fabricated across 5 separate plants scattered throughout western Pennsylvania. Traditional naval shipyards on the coasts had estimated 6 months minimum to build vessels of this size and complexity. Yet here, hundreds of miles from any ocean, a complete landing ship tank stood ready to slide into inland waters. Over 16,000 workers stepped back from the hull of LST-1, not traditional shipwrights, not experienced maritime craftsmen, but steelworkers, bridge builders, and heavy machinery operators who had learned welding techniques just weeks earlier. The crowd of military officials, journalists, and skeptical coastal shipyard representatives had gathered to witness something that violated every principle of naval construction. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Ships, especially combat vessels capable of crossing oceans, had always been built in coastal yards with access to deep water. The idea of constructing ocean-going warships in cornfield shipyards along inland rivers seemed absurd to maritime experts. Yet Vice Admiral Samuel Robinson, chief of the Bureau of Ships, stood watching a vessel emerge from facilities that had been empty mudflats just 9 months earlier. The mathematics of Allied amphibious warfare were being written not in naval architecture textbooks, but in production statistics that would shatter every assumption about where ships could be built, how quickly they could be assembled, and what kind of workforce could construct them. The transformation had begun in January 1942, when Admiral Robinson approached Dravo Corporation with preliminary designs for an invasion craft, unlike anything the company had ever built. Frank and Ralph Dravo, brothers who had graduated from Lehigh University with degrees in mechanical engineering and metallurgy, had spent 50 years building river barges, installing industrial machinery, and fabricating steel for bridges and dams. They had never built a naval vessel, never managed a coastal shipyard, and had spent their entire careers working with steel in ways that traditional maritime builders considered inappropriate for ship construction. Yet here stood executives of a river equipment company who had just accepted the Navy's challenge to build landing ships capable of crossing the Atlantic Ocean and driving directly onto enemy beaches to discharge tanks under fire. Traditional shipbuilders dismissed the entire concept as dangerously naive. Newport News Shipbuilding and Dry Dock Corporation, one of America's most prestigious yards, had reluctantly agreed to build the first LSTs using conventional methods, assuming their centuries of accumulated maritime wisdom would be essential to success. What none of them understood was that Dravo's complete ignorance of traditional shipbuilding would become the program's greatest advantage. Among those watching from the riverbank was Captain John Niedermeyer, the Bureau of Ships designer whose rough sketch had defined the LST's basic form just 10 months earlier. He had designed the vessel in November 1941, responding to British requirements for ships that could cross oceans with 14-foot draft for stability, then pump out massive ballast tanks to achieve a beachable draft of less than 4 feet. The ballast system alone represented unprecedented engineering complexity, adapted from fleet submarine technology. Niedermeyer had visited traditional coastal yards while developing specifications. Every maritime expert he consulted said building such vessels away from deep water made no sense. Ships needed to be launched into water deep enough to float them immediately. The Ohio River at Pittsburgh, even at high water, barely provided sufficient depth. Building at inland locations would require somehow transporting completed ships hundreds of miles down shallow, bridge-obstructed rivers to reach coastal ports for final fitting out. The concept seemed logistically impossible and economically wasteful. The journey from skepticism to revolution began in Dravo's offices overlooking the Monongahela River in January 1942. As company engineers examined the Navy's preliminary specifications, they recognized immediately that conventional shipbuilding methods would never meet wartime demands. The Navy needed hundreds of LSTs, needed them quickly, and needed them built without disrupting destroyer and carrier production at coastal yards. Dravo's chief engineer, having spent decades fabricating massive steel structures for bridges and industrial plants, saw something naval architects had missed. The LST's design, with its flat bottom, rectangular cross-section, and modular internal compartments, resembled a floating steel box more than a traditional ship. What naval designers considered an awkward compromise to meet contradictory requirements, Dravo engineers recognized as an ideal candidate for prefabrication and assembly line construction. The first real shock came with Dravo's proposal to build the ship in sections at existing steel fabrication plants scattered across western Pennsylvania, then transport these massive modules to a central assembly yard for final welding. Traditional ship construction proceeded sequentially from keel to deck in a single location. Every component was fabricated on-site or nearby, then installed in strict sequence as the hull gradually took shape over months. Dravo proposed treating the LST like a steel bridge, with different sections fabricated simultaneously at separate locations, then brought together for assembly in weeks rather than months. Vice Admiral Robinson examined the proposal with professional skepticism. His engineering staff at the Bureau of Ships had trained in naval architecture programs that emphasized traditional sequential construction. The idea of welding together massive prefabricated sections to create an ocean-going hull violated fundamental assumptions about structural integrity and quality control. Yet Robinson also recognized desperation. After Pearl Harbor, the strategic landscape had changed completely. The United States faced the necessity of amphibious invasions across both the Atlantic and Pacific. Operation Torch, the invasion of North Africa scheduled for November 1942, required landing craft that simply didn't exist yet. Traditional construction timelines, measuring 6 to 8 months per vessel, meant the invasions would fail before sufficient shipping could be built. The decision to approve Dravo's contract represented not confidence, but calculated risk born of absolute necessity. The Neville Island shipyard rose from swampy riverfront property between February and June 1942. Dravo's construction crews, experienced in building industrial facilities on impossible schedules, erected a facility that horrified traditional maritime engineers who visited for inspection. Instead of the permanent building ways and massive gantry cranes that characterized established shipyards, Neville Island featured something entirely different. The yard was laid out like an industrial assembly plant. Open staging areas surrounded multiple parallel building ways positioned perpendicular to the river. Railroad tracks crisscrossed the facility, designed to move massive steel sections weighing up to 75 tons. Overhead cranes, capable of lifting entire hull sections, stood every 100 feet. William Francis Gibbs, America's most respected naval architect whose firm had designed countless ships, including the SS United States, visited Neville Island in May 1942. His inspection report, marked confidential at the time, contained technical criticism mixed with grudging acknowledgement of industrial efficiency. Dravo has violated every principle of proper shipyard layout I learned in 4 decades of maritime experience. Their building ways are too short. Their crane capacity exceeds any reasonable requirement. Their facilities are designed for steel fabrication, not ship construction. Yet, I must admit the layout is optimized for exactly what they claim to do: rapid assembly of prefabricated sections into complete vessels. The arrival of workers provided the next phase of revolutionary change. Traditional coastal shipyards recruited from established maritime communities where skills passed from father to son across generations. Master shipwrights spent lifetimes perfecting their crafts. Unions carefully controlled who could perform which tasks. Dravo advertised in newspapers across Pennsylvania and Ohio, offering wages 20% above standard industrial rates and promising to train anyone willing to work. The company needed 16,000 workers immediately. Traditional maritime labor pools couldn't possibly supply such numbers. The first groups arrived at Neville Island in June 1942. Farmers from rural Pennsylvania, coal miners from West Virginia, steel workers laid off during Depression years, women whose husbands had shipped overseas. African Americans excluded from most skilled trades by discriminatory practices. None had ever built ships, most had never seen an ocean. Dravo's training program, developed in partnership with the Navy, simplified complex shipbuilding tasks into repeatable, specialized operations that could be taught in weeks rather than years. Workers didn't need to know how to build entire ships. They needed to know how to weld specific types of seams in specific locations, or how to install particular components using prescribed procedures, or how to operate cranes moving predetermined loads. The simplification of maritime construction into repeated, simple operations borrowed directly from automotive manufacturing proved devastatingly effective. By August 1942, Dravo employed over 10,000 workers at Neville Island, with fewer than 100 having any previous maritime experience. An additional 6,000 worked at American Bridge Company's new LST yard in Ambridge, 20 miles downriver. The prefabrication approach that traditional builders had dismissed proved its power through summer and fall 1942. Instead of building LSTs sequentially from keel to deck, Dravo's system fabricated entire sections simultaneously across 5 separate plants. While one crew assembled a bow section, including the massive bow doors and ramp at a plant in McKeesport, other crews built stern sections with propeller shafts and rudders at facilities in Ambridge. Engine rooms complete with diesel engines, reduction gears, and auxiliary machinery were assembled at yet another location. The massive tank deck, 230 feet long and 30 feet wide, was fabricated in huge sections at steel mills that normally produced bridge components. When sections were complete, railroad flat cars transported them to Neville Island, where welding crews joined them together on the building ways. Albert Kaufman, production supervisor at Neville Island, explained the efficiency in a 1943 interview with Industrial Management magazine. In traditional shipbuilding, you cannot install engines until the engine room is complete. You cannot build the engine room until the hull is substantially finished. Everything happens in sequence, one task waiting for another. Dravo's approach allows parallel production. While one crew welds hull plates at Neville Island, another crew installs engines in a prefabricated engine room section at a separate facility 15 miles away. When both are ready, we lift the completed engine room module into position using cranes and weld it in place. Tasks that required weeks in coastal yards now take days. The statistics of parallel production revealed manufacturing efficiency that seemed impossible to traditional builders. A conventional shipyard might assign 50 workers to install an LST's engines and reduction gears over 3 weeks, working in the cramped confines of a partially complete hull. Dravo's prefabrication approach assigned 200 workers to assemble complete engine room modules in open factory spaces over 10 days, then used cranes to position entire assemblies in single 8-hour operations. More disturbing still to traditional maritime authorities was the casual elimination of centuries-old shipbuilding practices. Ships had always been riveted, overlapping steel plates joined by thousands of heated pins hammered into place by skilled crews working in perfect coordination. The process was labor-intensive, time-consuming, and required craftsmen with years of experience. Dravo proposed welding the entire LST using electric arc techniques the company had mastered building steel structures and river barges. Traditional naval constructors considered welding fundamentally unsuitable for ocean-going vessels. The Royal Navy had prohibited welding on warship hulls after structural failures in early experiments. American coastal yards viewed welding as appropriate only for minor components and repairs. Admiral Robinson, reviewing Dravo's welding proposals in February 1942, faced a decision that would determine the entire program's viability. His correspondence preserved in National Archives files revealed the maritime establishment's concerns. Welding has never been proven reliable for large ship hull construction under combat conditions. European naval powers have rejected all welded hulls after experiencing failures. Dravo proposes we bet America's amphibious capability on welding techniques developed for river barges and bridge construction. Yet we have no alternatives. Riveting requires skilled labor we cannot supply in necessary numbers. Dravo's schedule depends absolutely on welding efficiency. The decision to approve all welded construction represented faith in industrial necessity overriding maritime conservatism. As construction progressed through summer 1942, Dravo's revolutionary approach produced results that silenced skeptics more effectively than any theoretical arguments. LST-1, laid down on June 10th, was launched September 7th. Just 90 days from first steel to launching, less than half the time Newport News required using traditional methods. The ship that slid into the Ohio River that Labor Day afternoon was welded, not riveted, built by workers trained in weeks, not decades. Assembled from sections fabricated 50 miles apart. Everything about LST-1 contradicted established maritime practice. Yet, when Navy inspectors examined the hull, they found workmanship meeting specifications. When the ship underwent sea trials after completion, it performed exactly as designed. When LST-1 crossed the Atlantic and participated in the North African invasion in November 1942, it proved seaworthy despite every expert prediction that welded inland-built ships would fail under ocean conditions. The psychological impact on traditional shipbuilders was immediate and profound. The same coastal yards that had dismissed Dravo as ignorant outsiders just months earlier now sent engineers to study Pittsburgh's approaches. Discussions that had been theoretical became urgently practical, as Navy planners calculated how many LSTs would be needed for forthcoming operations. The invasion of Sicily in July 1943 would require 74 LSTs. The eventual invasion of northern France would need more than 230. Operations across the Pacific would require hundreds more. Even with Newport News, Dravo, American Bridge, and 2 other yards now building LSTs, production fell dangerously short of requirements. The Navy's solution was radical: convert more inland facilities to LST construction, build cornfield shipyards along the Ohio, Mississippi, and Illinois rivers, use Dravo's prefabrication methods as the standard for the entire program, train tens of thousands more workers using simplified procedures proven at Neville Island. By January 1943, 5 major inland yards were building LSTs using Dravo's techniques: Missouri Valley Bridge and Iron Company in Evansville, Indiana, Chicago Bridge and Iron in Seneca, Illinois, American Bridge in Ambridge, Pennsylvania, Dravo at both Neville Island in Pittsburgh and a new facility in Wilmington, Delaware. Together, these cornfield shipyards would eventually produce 670 of the 1,051 LSTs built during the war, 63% of total production. The democratization of shipbuilding that Dravo enabled carried implications far beyond wartime emergency. By proving that ocean-going vessels could be built by trained industrial workers rather than requiring generational maritime craft expertise, the LST program challenged fundamental assumptions about labor, skill, and industrial organization. Traditional coastal shipyards had maintained their dominance through control of specialized knowledge and skilled labor. The craft traditions that governed maritime construction served as barriers to entry that protected established yards from competition. Dravo demonstrated that these barriers were artificial, that ships could be built wherever steel fabrication capability and industrial management expertise existed. The human story of transformation became visible in the faces and hands of workers who had never imagined building ships. Margaret Harrison, a former Pittsburgh secretary who became a welder at Neville Island, described her experience in a 1943 newspaper interview. 6 months ago, I was typing correspondence in an insurance office. Today, I weld hull plates on ships that will carry soldiers to invade Europe. The training took 3 weeks. I learned to strike an arc, control the puddle, and run straight beads on vertical surfaces. That's all I needed to know for my station. I weld the same seams on every ship. After 6 months, I can lay a perfect bead almost without thinking. The work is hard, the hours long, but I know what I'm building matters. Women comprised approximately 25% of Dravo's wartime workforce, a remarkable percentage for 1943. African American workers numbered in thousands, employed in skilled positions including welding, fitting, crane operation, and supervisory roles, unprecedented for the era. The integration wasn't driven by progressive social policy, but by desperate necessity. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The program needed workers faster than traditional labor pools could supply them. WWII hired whoever would work and trained them to perform essential tasks. The result was a workforce that looked like America rather than maritime tradition. Christmas 1942 provided a powerful demonstration of WWII's transformed industrial culture. While traditional coastal shipyards observed the holiday with days off, Neville Island maintained production schedules. Rather than simply demanding work, management provided Christmas dinners served in facility cafeterias with turkey, ham, and traditional accompaniments provided free to workers on shift. Local churches sent carolers. The Pittsburgh Symphony performed selections for workers during lunch breaks. Frank WWII himself visited the yards, walking production lines, shaking hands with welders, thanking workers personally for their service to the war effort. The gesture wasn't merely symbolic. WWII understood that the company's wartime success depended absolutely on maintaining morale and productivity among workers who could easily find employment elsewhere in Pittsburgh's booming steel industry. By spring 1943, the LST production system had stabilized into efficient routine. Construction time had fallen to approximately 4 months from keel laying to delivery. The Navy's urgent shortage was being addressed, though not yet solved. Sicily required 74 LSTs. Italian operations would need dozens more. The Pacific campaigns consumed LSTs faster than even accelerated production could replace them. Yet beneath the surface of apparent success, tensions were building. The Navy wanted faster production. WWII knew its current methods approached the limits of what sequential assembly could achieve. Traditional coastal yards, having reluctantly adopted WWII's prefabrication techniques, were catching up to Pittsburgh's production speeds. The next phase of revolution would require someone to question fundamental assumptions that even WWII's revolutionary approach had left unchallenged. The answer would come from an unexpected source, a modification to welding procedures so simple, so obvious in retrospect, that no engineer had thought to question whether the established sequence was optimal. The solution would emerge not from management offices or engineering departments, but from the production floor itself, observed by someone whose fresh eyes saw what experience had rendered invisible. That transformation would emerge not from a single breakthrough moment, but from the systematic refinement of 3 revolutionary innovations that WWII engineers developed through relentless analysis of production bottlenecks. The changes would reduce LST construction time from 4 months to 8 weeks, enabling the production surge necessary for D-Day and Pacific operations. The revolution was about to accelerate. Labor efficiency transformed dramatically through systematic refinement of procedures and accumulated worker experience. The first LSTs required approximately 700,000 worker hours to complete, representing the learning curve costs of an entirely new workforce, building an entirely new vessel type using entirely new methods. By mid-1944, average worker hours had fallen to 400,000 per ship at WWII's most efficient yards through multiple compounding factors. Workers gained proficiency through repetition. A welder who had completed the same seam on 50 consecutive hulls could execute that task in half the time required initially with superior quality. The specialization that traditional craftsmen criticized as limiting actually produced expertise through focused practice. Installation teams refined procedures after each ship, eliminating wasted motion and identifying optimal sequences. Supervisors documented improvements and distributed best practices across shifts and workstations. The learning curve effects were measurable and dramatic. Hull section fabrication that required 12 days initially dropped to 6 days by the 10th ship and 4 days by the 50th ship. Engine room installation improved from 8 days to 3 days over the same production volume. The cumulative effect of hundreds of small improvements across all construction phases produced total cycle time reductions that exceeded what management had believed possible. Cost efficiency matched schedule improvements despite rising wages and material prices through 1944. Initial LSTs cost approximately $2.2 million each, when accounting for all direct and allocated overhead expenses. By late 1944, costs had fallen to $1.8 million despite labor rates increasing 15% and steel prices rising 12%. The cost reduction reflected improved efficiency, reduced rework, and economies of scale as suppliers delivered standardized components in volume. Each LST displaced 4,080 tons fully loaded and could carry 2,100 tons of cargo, including 20 Sherman tanks or equivalent vehicles. The vessels could transport entire tank companies complete with all support equipment in postivities current, single voyages. The tank deck, 230 feet long and 30 feet wide, could accommodate virtually any American military vehicle, including trucks, half-tracks, artillery pieces, and construction equipment. The bow door design, 14 feet wide with a deployable ramp, enabled direct discharge onto beaches without pier facilities. This capability revolutionized amphibious warfare by eliminating the bottleneck of unloading into smaller craft for beach transfer. LSTs drove directly onto sand, opened doors, deployed ramps, and vehicles drove off ready for immediate combat operations. The ballast system that enabled both ocean crossing and beach landing proved remarkably sophisticated for vessels built so rapidly. When loaded for ocean transit, LSTs pumped ballast tanks full, achieving 14-foot draft for stability in heavy seas. Approaching landing areas, pumps evacuated ballast tanks, raising the hull until forward draft reached less than 4 feet, allowing access to beaches with gradual slopes. The system borrowed submarine technology but scaled to merchant vessel proportions, handling hundreds of tons of water transfer in controlled sequences. Training efficiency proved equally remarkable compared to traditional maritime apprenticeships. Dravo's schools trained welders in specific tasks, averaging 3 weeks from first instruction to production work. The fastest training produced productive workers in just 10 days for simple, repetitive operations. More complex positions like crane operators or ship fitters required 6 to 8 weeks of instruction. This compared to traditional maritime apprenticeships lasting 4 years for basic competency and 10 years for master craftsman status. The key difference was specialization versus comprehensive training. Traditional apprentices learned all aspects of ship construction, qualifying them to work anywhere in a vessel, but requiring years to master the breadth of knowledge. Dravo's workers mastered specific, repeatable tasks performed hundreds of times. A welder might never learn to read complex blueprints or understand ship stability calculations, but could execute perfect vertical seams on bulkheads through muscle memory developed over months of focused practice. The casualty rates among LSTs deployed in combat demonstrated their effectiveness despite skepticism about rapid construction and unconventional methods. Of 1,051 LSTs built, approximately 263 participated in combat operations across both theaters. 26 were lost to enemy action, representing a combat loss rate of 10% among vessels actually exposed to enemy fire, or 2.5% of total production. This compared favorably with traditional merchant shipping loss rates and proved that welded construction produced seaworthy combat-capable vessels. The losses came primarily from torpedo attacks, mine strikes, and kamikaze impacts rather than structural failures. Several LSTs absorbed tremendous damage and remained operational, demonstrating the structural integrity of seemingly crude construction. LST 523 struck a mine off Normandy that detonated directly under the hull, creating a hole large enough to drive a jeep through. The explosion should have broken the ship's back, the classic catastrophic failure mode for vessels with compromised longitudinal strength. Instead, the welded construction flexed, absorbed shock, and maintained structural continuity. Bulkheads held. The ship listed, but didn't capsize. Damage control teams sealed compartments and pumped continuously for 16 hours. LST 523 made Portsmouth under its own power and returned to service after 3 weeks of repairs. The West Lock disaster at Pearl Harbor in May 1944 provided a different test of LST construction integrity. LST-353 exploded while loading ammunition, triggering sympathetic detonations that destroyed 6 LSTs and damaged several others. The explosions killed 163 sailors and demonstrated the catastrophic consequences of ammunition handling accidents. Yet the fact that LSTs moored hundreds of feet from the initial blast survived with repairable damage testified to the structural robustness of seemingly hasty construction. Longevity statistics provided ultimate vindication of Dravo's construction approaches. LSTs, designed as emergency vessels with expected service lives of 5 years, proved remarkably durable. Many remained in active service for decades after the war. The U.S. Navy retained hundreds in mothball fleets as strategic reserves, periodically reactivating vessels for Korean War operations, Vietnam War logistics, and training exercises through the 1970s. LST-325, built at Evansville in October 1942, was decommissioned in 1946, reactivated for Korean War service, decommissioned again in 1961, then transferred to the Greek Navy, where it served until 1999. The vessel was returned to the United States in 2000, restored to operational condition by veterans who had served aboard LSTs during the war, and now operates as a museum ship that occasionally steams under its own power. After more than 80 years, the ship remains structurally sound, a testament to construction methods that maritime experts claimed would produce fragile vessels. Post-war careers of LSTs extended far beyond their designed lifespan and original military purpose. Of the approximately 775 LSTs that survived the war without being expended as targets or scrapped immediately, over 300 remained in U.S. Navy service through the 1950s. Many were sold to foreign navies, where they operated into the 1980s. Others converted to commercial service as small freighters, car ferries, and supply vessels serving remote Pacific islands. Several LSTs found second lives in surprising applications. One became a floating restaurant in San Francisco. Another served as a fish processing ship in Alaska. A third was intentionally sunk to create an artificial reef for marine habitat. The versatility of the basic design, originally optimized for a single wartime mission, enabled adaptation to diverse peacetime uses. The technological innovations developed during the LST program influenced industries far beyond maritime construction. The serrated channel reinforcement technique pioneered for hull plating became standard in industrial building construction, particularly for pre-engineered metal buildings and warehouse structures. The geometric strength provided by corrugated profiles enabled spanning larger distances with less material. The jig and manipulation systems refined at Dravo influenced heavy manufacturing across sectors. Steel fabrication plants, building bridges, pressure vessels, and industrial equipment adopted similar approaches for positioning large assemblies during welding and machining. The principle that workers should remain in optimal positions while work rotated to them became foundational in ergonomic workplace design. The transfer buggy concept for moving massive assemblies through progressive workstations influenced automotive manufacturing, aircraft production, and heavy equipment assembly. The idea that large, complex products could move through specialized stations, rather than being built in fixed positions, enabled the production line approaches that characterized post-war American manufacturing dominance. The organizational principles of rapid training, specialized tasks, and systematic process improvement became foundational concepts in operations management and industrial engineering education. Business schools studying American industrial competitiveness identified the LST program as a crucial case study in rapid capability development and workforce transformation. Professor John Kenneth Galbraith, analyzing American wartime production in his 1952 Economic History, identified the LST program as exemplifying crucial lessons about industrial capacity and organizational capability. The United States entered World War II with minimal amphibious ship construction capability. Traditional maritime authorities said building landing ships at inland locations made no economic sense. Within 18 months, inland yards were producing more amphibious vessels than the rest of the world combined. This demonstrated that industrial capacity is not fixed by existing facilities or traditional practices, but can be created rapidly when necessity demands and innovation is permitted. The lesson has relevance beyond wartime emergency. It proves that perceived limitations often reflect organizational and conceptual constraints rather than physical impossibilities. The workers themselves carried forward the most important legacy. The shipyards gave thousands of young people, especially women and minorities, opportunities to develop capabilities they would never have accessed through conventional career paths. Those opportunities opened doors that stayed open for the rest of their lives. Margaret Harrison, the former secretary who became a welder at Neville Island, used her wartime experience to establish a small welding contractor business after the war. She employed other women who had learned the trade at Dravo, specializing in industrial maintenance and repair work. Her company operated successfully for 35 years, eventually employing 20 workers and serving major Pittsburgh manufacturers. In a 1978 interview, she reflected on how wartime opportunity had transformed her life. "I never imagined running a business. I expected to work as a secretary until I married, then become a housewife. The war changed everything. I learned I could do hard physical work and do it well. I learned I could solve technical problems and manage complex projects. After the war, I couldn't go back to typing letters for men who earned 3 times my wages while knowing less than I did. The welding skills gave me options. The confidence gave me courage to pursue opportunities I would never have considered before the war." Thomas Robinson, the African-American crane operator, used his wartime training to become a heavy equipment operator in the post-war construction boom. He worked on projects building the Pennsylvania Turnpike expansion, the Fort Pitt Tunnel, and numerous bridges across western Pennsylvania. In a 1965 interview, he described how Dravo had changed his career trajectory. "Before the war, I was trapped in laborer positions, regardless of my capabilities. White employers assumed black men couldn't handle skilled technical work. Dravo hired me because they needed workers, not because they believed in equality. But the result was the same. I proved I could operate complex equipment, manage responsibility, and perform skilled work as well as anyone. After the war, I had references, experience, and confidence. Employers who might have rejected me based on race had to acknowledge my documented capabilities. The war didn't end discrimination, but it gave me tools to overcome barriers that would have been insurmountable otherwise. The social transformation enabled by wartime production extended beyond individual success stories. The demonstration that women could perform heavy industrial work and minorities could handle skilled technical positions challenged assumptions that had maintained discriminatory practices for generations. The changes weren't permanent or universal, but they created precedents and proved possibilities that subsequent civil rights movements would build upon. The LST story ultimately stands as testament to profound truths about human capability and industrial possibility. The ships themselves, while crucial to Allied victory, mattered less than what their construction proved. Ordinary people given training and opportunity could achieve extraordinary results. Complex products previously requiring years of craft tradition could be manufactured in weeks using systematized processes. Industries resistant to change for centuries could be revolutionized in months when necessity and innovation combined. The transformation didn't happen through single breakthrough moments or individual genius insights. It emerged from systematic questioning of assumptions, willingness to challenge traditional practices, and relentless focus on solving specific problems. Dravo succeeded not by discovering revolutionary new technologies, but by applying existing industrial manufacturing principles to a domain that had always exempted itself from such approaches. The maritime establishment that dismissed Dravo as ignorant outsiders in 1942 spent decades after 1945 studying and implementing their techniques. The workers who learned to weld and fit and fabricate carried those skills and that confidence into peacetime careers that rebuilt America's post-war economy. The approaches pioneered under wartime emergency became peacetime standards that influenced manufacturing across industries and around the world. The LSTs are mostly gone now, scrapped decades ago, converted to other uses, or resting on ocean floors. But the revolution they represented endures in every modern shipyard, in every manufacturing facility that uses progressive assembly, in every training program that teaches specific skills quickly rather than comprehensive expertise slowly, and in every manager who questions whether impossible truly means impossible or simply means nobody has figured out how yet. That is Dravo's enduring legacy, carved not in steel but in transformed understanding of what dedicated people can accomplish when freed from constraints of tradition and challenged to attempt what experts claim cannot be done. From January 1942, when Robinson approached the Dravo brothers about building ships they had never constructed, to September 1945, when the last LST was delivered, to the decades of influence that followed, the program proved that industrial revolutions happen not through incremental improvements, but through fundamental reimagining of what is possible. The 1,051 LSTs built between 1942 and 1945 carried more than cargo and soldiers across oceans. They carried proof that human ingenuity, when unshackled from tradition and empowered by necessity, can accomplish the seemingly impossible. They demonstrated that the greatest limitations are often not physical or technical but conceptual, not about what cannot be done but about what established authorities claim should not be attempted. The story of how industrial manufacturing principles transformed ship construction from 6-month craft production to 8-week assembly line efficiency remains relevant wherever industries face challenges that conventional wisdom claims impossible. The lesson demonstrated in the shipyards of Pittsburgh and validated by 1,051 completed vessels echoes across decades. Progress requires questioning accepted limits. Transformation demands challenging traditional practices, and human potential exceeds conventional expectations when properly organized, trained, and empowered to prove what dedicated people can achieve. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.